Hey everyone, welcome to the fourth vlog of my computer vision series. In my previous vlog, I talked about object detection exercise. I also gave you a brief overview of YOLO model, which is a very widely popular model to perform object detection exercise in computer vision applications. If you missed that vlog, I'll definitely recommend you to go back to my channel and watch that vlog before you move further with this one. And please don't forget to like and subscribe to my channel as more contents on computer vision and data science are forthcoming. So in today's vlog, I'll talk about image classification. So what is image classification? So in a nutshell, image classification is a mechanism to categorize and label a group of pixels or vector in a static image based on specific rule. Like for example, in my previous blog, I gave you an overview of how our autonomous car detects objects on the street. So how did autonomous car classify that object? How that computer vision or underlying computer vision model of that autonomous car identify that object belongs to a car, sedan car, or it belongs to a truck, or even it belongs to a traffic signal. So that kind of mechanism performed by image classification technique, which is nothing but an underlying neural network model that categorize an object based on specific set of features and their corresponding rules. So for example, like if you process an image through a neural network model, then it will extract all the features corresponding to that image and it will memorize those features. So in future, if you try to predict a similar object using that same neural network model, then neural network model will classify that object belongs to that particular category. So in my next section, I'll show you that how a computer vision model classify an image belongs to a cat or dog based on certain features of their rules. Okay, so let's check out that how you can perform your first image classification exercise using a Tensorflow neural network model in order to identify a cat and a dog. In this section, I'll show you how you can perform an image classification exercise using binary mechanism on a dataset comprised of cat and dog. The neural network model that I'm going to build is going to classify an image and identify whether that image belongs to cat or dog. So at the first phase, I need to upload a data set comprised of cat and dog images. So I uploaded the images in a zip format to the temp directory of my Google Colab. In addition to that, I also have to import some libraries related to TensorFlow because those libraries will be useful to perform the image classification exercise in the later stage. After I upload the data set, I need to categorize the images into two different types. One set of images will be used for training purpose, and the other set of images will be used for validation purpose. So that part I'm performing over here. In addition to segregating the images into train and validation based directories, I do also have to make sure that in the train directories, I do have two subdirectories. One belongs to cats and one belongs to dogs images. So that means you actually have to split the images based on their labels. Like for example, if you print the 10 images from any specific directory, you would see that all the cat images starts with the label cat and the dog images start with the label dog. The reason we do perform this the image processing, pre-processing in such a way so that a model would be able to identify the images easily and they can extract the features accordingly from any cat or dog image. The next step is to normalize the image, right? Because so when we perform any image classification exercise, we always need to remember that any pixel range is between 0 to 255. So we have to normalize that image in order to make sure the pixel range falls between that 0 to 255 range. So we perform that using an image data generator function. The next step is we need to make sure that our image, all the images are following a standard size. So what we do is that we actually transform all the image into 150 to 150 target size. For your exam, for your exercise, you can change the target size. There is no rule of thumb over there. But for my case, I just transform all the images into a standard size of 150 by 150. You need to perform this image generator image transformation on both train and validation directory. So you know, to make sure that all the images are of all the train and validation images follow a certain size and standard. As I mentioned previously, that here we're performing only two classification. The classification level is 2 over here because we are only identifying images based on 2 different categories, cat and dog. So that means we're performing binary classification here. In future, you may have to perform different kind of image classification where you have to categorize the images into multiple categories, like more than 2 categories. So in those cases, we usually call it as a multi-class classification. Now, if you want to visualize some of the images, you can run this particular program with the particular line of code, and it will show you the number of images. As you can see, there are tons of pictures of cats and dogs are lined up. So these are the images are going to be processed through the neural network model. Now, next, to talk about the model. So in this particular image articulation exercise, I'm going to use a regular sequential model. So this is so you can use a TensorFlow library to build that sequential model. The sequential model will have 1, 2, 3, 4 different convolutional network followed by a max pool layer. So the reason actually I'm using a combination of convolutional and max pool layer so that I can downsize or downsample the image size to certain level that when you are going to flatten that model finally, then you are not going to end up with a lot of nodes. So that's why I started with 32 input dimension, and slowly I increased that convolutional layer nodes, but also I make sure that I apply the max pool layer in order to downsample the dimension. So if you are a little confused about this convolutional layer architecture, I'll definitely recommend you to go back to my channel and look for a video where I talked about convolutional layer network architecture. So, so now after you flatten the convolutional layer, then you have to process all the images through a linear layer node. So here I used the activation function ReLU, and we actually have one linear layer, and the dense layer output would be 1. The reason the output is 1 over here because for this particular exercise, I'm performing 2 binary class. So it will be either a cat or dog, right? So in that case, your output layer should be comprised of one particular output dimension. Okay. So now the next thing, so once we finalize the model, so I'm going to run this model in order to make sure that the model has been processed. So now we have this model comprised of multi-layers of convolutional and max pool layers, followed by a dense layer. The next step is model hyperparemeters. So we need to make sure that what kind of hyperparemeters are we going to use for this particular exercise. So since it's a binary classification, that's why we use a loss function binary cross entropy. If you perform multi-class classification, then you have to use different kind of cross entropy function. For optimizer, I'm using RMS prop here, but you are entitled to use any other optimizers like SGD or Adam or any sort of other optimizers for your exercise. So I would definitely recommend you to try different optimizers and to make sure that optimizers and also learning rate to make sure that you find out the optimal the hyperparameters which will provide the maximum accuracy from the model. The next step, I implement callback function. The reason we have a callback function because no model is perfect, so it's very difficult to achieve 100% accuracy from any model. And we should not target to achieve 100% accuracy from any model. So here, but that doesn't mean that you're gonna let your model run forever. So in that case, you need to set baseline model accuracy matrix. So here I'm actually setting up a baseline accuracy score, which is 0.9970. If our model would achieve that particular accuracy score during the training time, then it will stop right away. It will not process further. That's why I implemented the callback function. So it will actually eventually it will reduce some model training time. So the next step is run the model. Now this process will take some time. So here actually I asked the model to run for like a 50 iterations or epochs. So in some cases, since I already implemented the callback function, it's possible that a model would stop training after it achieves that accuracy, the baseline accuracy score that is set in the callback function. So as you can see, that first iteration been completed, and the model loss is 0.6671, accuracy is 0.5420. We definitely expect that this accuracy will go up in further epoch runs, and loss count will decrease gradually. As you can see that all the epochs taking like 9 to 10 seconds, so it's very fast. And so many times it will take not much time for model to process the train during training time. And most of the time, the model training time increased depends upon the number of images persisted in the data set. If you are dealing with like thousands of images for training the model, then obviously your model will not be able to train faster. And so many times you have to use a different configuration. Like for example, like for this particular exercise, I'm using a hardware accelerator as GPU. So I'm using actually GPU hardware accelerator. But if you are planning to like gradually increase, planning to increase your image data set, image volumes, then in that case, you may have to use kind of higher hardware accelerator like GPU, or you have to perform your exercise on Google Colab Pro, which provides better system configuration than the regular version of Google Colab. As you can see that the epoch run is progressing pretty well. And as you can see, the accuracy is going up. It started from 0.5420, now it's gradually going up. Now it's like 0.8470. So it's not very further away to meet that baseline accuracy score that is set in the callback function. And as you can see, as that accuracy score is going up, the loss is also going down. So this one is so this particular accuracy loss belongs to the training image. Now, if you want to check how the valuation loss and accuracy look like, so here you can see the valuation accuracy started from 0.5980, and it also gradually increasing, not at the same rate as the training accuracy, but it also increasing rapidly. So that means the model is training well. And also one more thing you need to make sure, when I mentioned the fact that sometimes you have to set the baseline accuracy score to a certain level, you can't expect that the model should accurately fit and it will yield accuracy 100%. But if it does, then that means sometimes model is overfitting. It's like because so many times it happens the data is exactly fit to the training model, the training data exactly fit to the model, which eventually lead us to a model overfitting issue. But in that case, the model failed to categorize any object on the unseen test data. So the model overfitting is a big issue. I'll talk about the model overfitting in one of my forthcoming vlogs, but always make sure that your model won't reach that 100% accuracy. Because most of the time, if you achieve 100% accuracy, that means your model is overfitting against the training data. So as you can see, we almost there. Right now our training accuracy is around 98%. So hopefully it will run for a few more epochs before it meets that validation accuracy, baseline validation accuracy. And if you see, on the other hand, the validation accuracy, it's growing, it's kind of like it's increasing, but it's not increasing at the same rate as training accuracy. It's possible because most of the cases, the validation accuracy is, it's considered as an unseen test data. So you can't expect the validation accuracy would go up a lot. Okay, but in some cases, you can definitely tweak the model and see if you can get better validation accuracy. So as you can see that it's going pretty well, and it's almost reaching that stage. All right. So as you can see that the callback function worked as the model stopped training after 33rd epoch. So that means if the model reach that baseline validation accuracy, it will stop training, which is why we implemented I implemented the callback function at the beginning. Now let's see how this validation loss or validation accuracy will look like as opposed to training loss and training accuracy. So this is a training and validation accuracy plot. As you can see, the training plot is steadily increasing, but after certain epoch, it kind of being stagnant because it's almost getting close to that baseline validation test accuracy. Whereas the validation accuracy remain kind of same within that around 75% zone. So if we can check that if we can tweak the model in order to improve the validation accuracy. But right now, a 75 to 80% validation accuracy, it's well enough to meet some sort of baseline metrics. Now, the next is training loss. As you can see, the training loss is kind of gradually decreasing. But the problem over here is the validation loss. You can see the validation loss is increasing quite rapidly, which is not a good sign. So that means the model is not performing well on the unseen test data. So how would you eradicate this kind of pitfalls? So in that case, there is a technique called image augmentation, which you can apply to your model, which you can apply to the training images before you process it through the model. So image augmentation would help you to alleviate some of these in the validation loss issues. So the validation loss, increasing validation loss is not a good sign for a model to perform well in the real world. Now, the next thing is let's test this model. Okay, so I'm gonna choose a cat or dog images and see if this model would be able to identify those images perfectly. So I'm going to process a cat image first. So I just uploaded a cat image, and as you can see, that model is able to identify the image as cat. Let's check out another one. So now I'm going to upload a dog image. There you go. As you can see, the model was able to identify the dog image perfectly fine. So that's all for now. So as you can see, this is a very primitive image classification exercise where it just kind of processes the model using a set of cat and dog images and make it understand that how it can identify an image cat and a dog separately. So that's all for now. I will definitely recommend you to check the video caption where I shared the GitHub link of the source code, and feel free to ask me any question. Feel free to share your comments in the video caption. So I'll be happy to answer, and I'll definitely recommend you to perform similar sort of image classification exercise using different image datasets. There are tons of datasets out there. Just download an image dataset from Kaggle and just do your own image classification work. So that's all for today. I'll definitely recommend you to check the Jupyter notebook in my GitHub account, and also try to implement the same model using different data set. You're allowed to change the model. You can add more convolution layer or edit the current layers as well. You can always tweak the model hyperparemeters and also apply data augmentation technique in order to improve the validation accuracy. There is no rule of thumb over there. You can always try different trial and error approach in order to come up with the best model. And always make sure that you have ample number of images to process through the neural network model. In my next video, I'll talk about another very important computer vision technique called face detection. So stay tuned for that. And please don't forget to like and subscribe to my channel as more contents are forthcoming. So till then, goodbye.